Welcome to our discussion. Today we'll be exploring a new open-source large language model, LLM, called Hunyuan-Large, developed by Tencent. This model boasts a massive 389 billion parameters and 52 billion activated parameters, making it a significant player in the field. What are the key innovations that set Hunyuan-Large apart?
Hunyuan-Large distinguishes itself through several key innovations. Firstly, it leverages a massive amount of synthetic data, 1.5 trillion tokens, in addition to its natural language data. This significantly enhances the model's ability to learn richer representations and generalize better. Secondly, it employs a sophisticated mixed expert routing strategy, combining shared and specialized experts for efficient processing. Finally, it incorporates key-value cache compression and an expert-specific learning rate strategy for improved efficiency and performance.
The use of synthetic data is interesting. Can you elaborate on how this data was generated and its impact on the model's performance?
The synthetic data was created through a four-step process: instruction generation, instruction evolution, response generation, and response filtering. This ensured high quality and diversity. The impact is substantial. The model demonstrates superior performance across various benchmarks compared to models trained solely on natural data.
You mentioned a mixed expert routing strategy. How does this differ from traditional approaches, and what are the benefits?
Traditional MO models often use a simple top-cake routing strategy. Hunyuan-Large uses a shared expert for common knowledge and specialized experts for domain-specific knowledge, activating only the top-scoring specialized expert for each token. This improves efficiency and allows for better handling of diverse tasks. We also introduced a recycle routing strategy to reallocate tokens initially assigned to overloaded experts, preventing information loss.
The paper also discusses key-value cache compression. How does this improve the model's efficiency?
We combined grouped query attention, GQA, and cross-layer attention, CLA, to reduce the memory footprint of the key-value cache. This significantly improves inference efficiency without sacrificing performance. The GQA-CLA technique saves nearly 95% of KV cache compared to traditional methods.
The model's performance is impressive. What benchmarks were used to evaluate Hunyuan-Large, and how did it perform?
We evaluated Hunyuan-Large on a wide range of benchmarks, including MMLU, Common Sense QA, GSM-8K, Human Evil, and several Chinese language benchmarks. It consistently outperformed comparable models, including LL 3.170B, and even showed comparable performance to the much larger LL 3.1405B.
The paper mentions explorations into Mohs scaling laws. What insights did this provide for the development of Hunyuan-Large?
Our analysis helped determine the optimal number of activated parameters and the amount of training data needed for optimal performance within a given compute budget. This guided our choices for Hunyuan-Large's architecture and training process.
What about the post-training phase? How was the model further refined?
Post-training involved supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF, using a large dataset of instructions and responses. This improved task-specific capabilities and aligned the model more closely with human preferences.
The paper highlights the importance of data quality in both pre-training and post-training. What measures were taken to ensure high-quality data?
Rigorous data filtering was crucial. We used rule-based filtering, model-based filtering using a critique model, and human-based filtering to remove low-quality or biased data. For the SFT data, we also focused on instruction extraction, generalization, and balancing to ensure a diverse and representative dataset.
The model's ability to handle long contexts, up to 256K tokens, is also noteworthy. How is this achieved?
We employed a dedicated long context pre-training phase, gradually increasing the sequence length. We also used rotary position embedding, ROPE, and scaled the base frequency to improve the model's ability to handle long sequences.
What are the key takeaways from the Hunyuan-Large research?
Hunyuan-Large demonstrates that a well-designed MO model, combined with high-quality data and efficient training strategies, can achieve state-of-the-art performance. The open sourcing of this model is a significant contribution to the LLM community.
The paper mentions several future research directions. Can you briefly touch upon those?
Future work could focus on further improving the efficiency of MO models, exploring new routing strategies, and developing more sophisticated methods for generating high-quality synthetic data. Research into better alignment techniques and addressing potential biases is also important.
The model's performance on long context tasks was evaluated using both established benchmarks and a new benchmark called PenguinScrolls. What makes PenguinScrolls unique?
PenguinScrolls addresses limitations in existing benchmarks by including diverse, real-world, long-form texts, fine-grained task types, multi-turn dialogues, and multilingual support. It provides a more realistic and comprehensive evaluation of long context capabilities.
This has been a fascinating discussion on Hunyuan-Large. Thank you for sharing your insights.